Okay, so today I'm going to be discussing the following problem here on the screen, and that is to draw a 2-ethyl cyclohexane 1-ol in 4 of its stereoisomers, along with that labeling each one of these with stereocenters, either R or S, and then finally explaining the relationships between each of the molecules, whether they are enantiomers or diastereomers. So to start, I'm going to draw the general molecule here without any sort of different bonds on it. So we're going to have a cyclohexane, which is going to look a little bit like this, just drawing a hexagon on the paper here. Once we have that, we have a 1-ol, which tells us that wherever we decide to have the first one carbon, we're going to draw a OH group off of it. So that'll look a little bit like that. And then we're going to have an ethyl group coming off of the 2 carbon, which will look something a little bit like that. And of course, we could kind of label this just to know. So we have 1 here, 2 here, and obviously 3, 4, 5, 6, which isn't as important. But, you know, you could kind of see that there. Now, following this, we have to think about what kind of stereoisomers we want to draw. So these would fall into the categories of an enantiomer, where we change the direction of all the bonds. And along with that, diastereomers, where we would change all but one of the bonds and which direction they're going, as far as whether it's a wedge, which would be coming up out of the paper at us, or a dashed line here. So this would be going down into the plane, this would be going up out of the plane. So for now, we kind of have to decide the stereochemistry on it because we're not explicitly given that in the problem, but we could go ahead and just say that we have this here and this here, just to go ahead and get us started, and then start to get into drawing our stereoisomers. So the first thing we could do is actually draw the enantiomer, which, like I said, is going to be flipping all of the bonds, so that would look something like this. So right here, instead of a wedge, we would have a dash with the same OH, and then right here we'd also have another dashed line, and that is our enantiomer of our original structure up there. Following that, we could draw 3 diastereomers. So the way that we know the amount of structures that we're actually going to have is 2 to the n, where n is the number of bonds. So there's going to be 4 total molecules. So one way we could draw one of the diastereomers is to go ahead and just flip this top bond here into a wedge. So we have an OH, and then we could keep the wedge on the ethyl group, which will look a little bit something like this. We could also draw this molecule again and draw it with a wedge on the top with the same, like I said, OH, and then we're going to have the wedge coming out here. And this will actually be all 4 possible structures for this. We have 4 structures total, and that is what we would expect when we are drawing these kinds of things, these kinds of molecules. Again, if we had a different group coming off of here and we had 3 bonds, we would actually have 8 total different molecule orientations that we could draw, but you know, this one's pretty easy because we don't have that many choices in general. So now I'm going to go ahead and clear this page and redraw the molecules, and we could talk about some stereochemistry and where we would find our stereocenters. And bringing us back here, here are all the molecules we had on the first page I showed. So this would be the original molecule. This would be the enantiomer of that molecule. And here are 2 different diastereomers of that first original molecule. So now we have to start thinking about the R or S configuration of these different stereocenters in these molecules, right? So the first thing we have to do is identify our stereocenters, which we know will be right here due to the fact that there is a hidden hydrogen coming off of here, along with having one here, which would also have a hidden hydrogen. Now remember that a stereocenter is anything bonded to 4 different things, so this one is definitely bonded to 4 different things. This one is also definitely bonded to 4 different things if you follow the chain down to the different carbons, and that would make it so that in all of our other molecules we have stereocenters at the exact same points, but with different attachments of the hydrogen group depending on which direction the original bond is going. So on this one, the OH group is coming up out of the page at us, so we know that the hydrogen must be in the opposite direction, going back down into the plane away from us. So here we have an OH group that's going to be coming back into the page, so our hydrogen has to be the opposite of that, therefore coming up out of the page at us. And the same can be said for the ethyl group over here. And kind of filling in, obviously, going back into the page, right here, coming out of the page. And obviously over here, coming out of the page, and going into the page. So now that we have all of our hydrogens drawn in, we can start numbering this thing. And we are going to go ahead and start here. So the way we number is, first of all, the lightest group, which in this case would be hydrogen, is given a 4. And the heaviest group over here, which would be the OH, would be given a 1. And now we have to determine which side of this molecule is going to get priority. And again, bigger, heavier groups are going to get that priority number. So we're going to go ahead and look here. Right here we have a carbon with 2 hidden hydrogens coming off of it. And over here we have this big group with an ethyl group coming off of it. So we're going to go ahead and number this side 2 because it has higher priority and is therefore bigger. And we're also going to number this side over here 3 since it is smaller. And we're going to kind of draw in a little bit of a line here indicating the direction in which we are traveling with the actual, stereocenter. So when naming, in terms of the R and S configuration, R is always going to be clockwise. And S is always going to be counterclockwise. But there is a bit of a disparity that comes in when it comes to actually numbering this molecule over here, which we're going to go ahead and do. And it's numbered the exact same way. The hydrogen gets a 4, OH gets a 1, this side is a 3, this side is a 2, and the line will kind of go like this, the same exact direction. But instead, we have to look at this a little bit differently because we actually want the hydrogen over here, which is on both of these, just in different directions, to actually be going back into the page. This is more of just an orientation type deal, and what you could do is, reflect this over here and redraw the whole molecule so that the OH is, pointing up like this, and so that the hydrogen would be going back into the page. I'm not going to redraw that whole thing because, honestly, in my opinion, the better way to do this is to just flip the R to an S or the S to an R. So over here we have a clockwise movement, so that would look R, but it's actually S, due to the fact that our hydrogen is coming up at us out of the page. So with that logic in place, we could also say that this stereocenter over here is going to be R configuration because it is clockwise, but the H is going back into the page. And the same logic applies. Over here we have a hydrogen going back into the page. That's great. We don't have to flip anything. This ethyl group is the biggest group. Now this big OH is going to get the 2 priority. This down here, which is going to be the same as over there with a carbon with 2 hydrogens coming off of it, is going to get the lower priority of 3, 1 to 2 to 3. And in this case, we're actually going counterclockwise. So this is going to be S. Now coming back over to this quote-unquote problematic enantiomer, we're going to go ahead and do the same thing again. So the numbering again is the same. Hydrogen gets 4, ethyl gets 1. This side is going to get the 2, this side is going to get the 3, and we draw in our arrow, and it looks like it's S, but since we know that this hydrogen isn't in the correct orientation, it is actually R. So this stereocenter over here is an R, this one is an S. So when it comes to actually naming this thing, we would call it 1R, because our first group up here is in the R orientation. 2S, because our second group, or I guess our second, group also stereocenter is the S orientation, and we would just leave the rest of the name, which is 2-ethyl cyclohexan 1-ol. So that would be the name of this first molecule here, and the only thing that we're going to be changing, since this is still a 2-ethyl cyclohexan 1-ol, is this first configuration part, which over here would end up being 1S, because again, our stereocenter here is S, first group, 2R, same reasoning, and then the rest of the name that is right here. So now we can go ahead and move down into the diastereomers, and do the exact same process. So I'm going to go ahead and clean this up a little bit just for clarity's sake here. So just like in the first one, we number this actually the exact same, since it is literally this same group that we saw in the original. That's going to be 1, that's going to be 4, this is going to be 3, this is going to be 2. Arrow goes along here. The H is back in the correct position, so this is going to be R. And if you notice, we just did the exact same thing that we did here. So if we look at this right here, we can see that, oh, all the way up here, we've already numbered and named this thing, and we said that it was R, and the same logic applies. So this would be 1R, 2R, and the rest of the name, which would be 2-ethyl cyclohexane 1-ol. So the whole name would be 1R, 2R, 2-ethyl cyclohexane 1-ol. And we could do the same thing over here. So if we notice all the way up here, we had S on this exact orientation. Go ahead and take that. And we also over here had S on this orientation, because these are going to match. So then we're going to also have S. So just with everything else, it's going to be 1S, 2S, and then the rest of the name, 2-ethyl cyclohexane 1-ol. So that is our stereochemistry there with the R and S direction. Now we kind of have to talk about the relationships between all of these molecules and how they all kind of connect to each other. So again, I'm going to go ahead and redraw all these molecules just so that we don't have to work with this big ugly mess that I've made here. Okay, so with the power of editing, we are back with our 4 original molecules, and we're going to go ahead and talk about the relationships between all of them. So right over here, we have our original molecule, and we said that the relationship between this molecule and this molecule was enantiomer. This was because we flipped the direction of both of the bonds and we changed everything, which in turn would be the definition of what an enantiomer is. Along with that, earlier in the video, we also said that the relationship between this molecule and this molecule was diastereomer. And the relationship between this molecule and this molecule was also diastereomer. The reason for this was the fact that we changed only one bond and we didn't change everything as we did with the enantiomer, and that's kind of what's going to differentiate between the two. But wait, we could actually look at these right 2 molecules and also make a relationship connection as well, because we could look at this first molecule here and say, hey, this has a wedge right here that changed to a dash, and it also has a dash over here that changed to a wedge. So since everything changed, these are also enantiomers. Enantiomers. So there's that. We could then also say that both of these over here have the relationship of diastereomer. Since we only changed one thing, this little wedge changed to a line, but the line over here remained. And the same thing can be said here. And we could also say this because while this dashed over here changed to a wedge, this dashed line ended up staying in both structures. So we only changed one thing. So that's basically all the relationships that we can see here, and that pretty much completes the problem. Again, these two are enantiomers of each other. These two are enantiomers of each other. We could also look at the diastereomer relations between these molecules, in which only one bond direction is flipped. So if we're looking at the diastereomers of this molecule, we have these two. And if we're looking at the diastereomers of this molecule right here, we would have over here this molecule, because we only flipped one, and this molecule because we would have only flipped one as well. Additionally, the diastereomers of this molecule would be this molecule and this molecule. These two right here would be enantiomers. The diastereomers of this molecule would be both this molecule and this molecule. And as you can see, it gets pretty convoluted pretty fast. So I'll go ahead and redraw one of these relationships so you could kind of set it as an example. So we'll go ahead and do this one and this one. So for this first one here, we would have the OH going back along with the ethyl going back. So to draw the enantiomer of this, we would just flip everything. So we have a wedge here. And on this corner that's not so greatly drawn in, we're also going to have a wedge for the ethyl. So that would be the enantiomer. And then to make a diastereomer, we just have to flip only one of the originals, so we can make this top one a wedge for the OH and keep this one as dashes. Or we could do the inverse of that, which would look like this, in which we have dashes on the top for the OH and a wedge down here for the ethyl group. And like I said, if we were doing this one all the way over here, this is our starting molecule, in which we have OH going with the wedge up, and the ethyl group over here going back into the page with the dashes. And again, to make an enantiomer, all we do is flip both. So flip that one, flip that one. Over here, as we can see, wedge goes to dashed. As we can see with this one as well, dashed goes to wedge. And then to go ahead and make diastereomers, we only have to change one direction of the bond on this original molecule. So we could keep this one with the OH a wedge and make the ethyl a wedge, or we can make it so that both are dashes. Because again, we wouldn't be changing this one, we'd only be changing that one. So that's pretty much the entire problem, along with naming these kinds of things. I'll see if I could pull up this original sheet. So yeah, this was our question. We drew a 2-ethylcyclohexane 1-ol and 4 of its stereoisomers, along with labeling the stereocenters R or S, which was done over here, which is a big old mess. So I'm going to go ahead and hide that, but that is in the video. And then we explain the relationships between each of the molecules, whether they're enantiomers or diastereomers. And again, enantiomers would change direction of all the bonds, and the diastereomers would be all but one.